So this is about calculating the average atomic mass. Okay, this video, page 58.
Isotopes, and the masses of gallium-69. Gallium has two stable isotopes, and the masses of gallium-69, which is 60.11% abundant, and gallium-71, 39.89% abundant, are 68.926 AMU and 70.925 respectively. You know what respectively means? It means we've got two masses here and two atoms here. So respectively means the first of these masses goes with the first atom mentioned, and then the second one of these masses goes with the second atom mentioned. So don't let that term throw you off. So that's what respectively means.
Okay, we're just going to pause. Do you guys know what the term abundant means? If I say 60.11% abundant, that means, sorry? Yeah, abundant means there's a lot of it. So, but if I actually give a percentage with the abundance, what it means is gallium-69, the first one, is 60.11% abundant. That means out of every single gallium atom in the universe, 60.11% of them have a mass of 69. Yes? In fact, the mass is actually a little bit smaller. It is actually 68.926, so a little bit smaller than 69, okay? And that has something to do with E equals mc squared, and I don't really understand it, so, you know, go to your third year chemistry professor for that one when you go to university, okay? We'll just know that sometimes the mass of an isotope is somewhat smaller than its predicted mass based on the number of protons and neutrons. So gallium-71, that's the other isotope. Again, its mass is somewhat smaller, just a tiny bit smaller than 71. It's 70.925 AMU. And if you have 60.11% abundance of the one, then you would have to subtract that number from 100 and you would get 39.89% for the other isotope. So we understand what that means now, and we're going to carry on.
Anyway, calculate the average atomic mass of gallium. So to do this, we're going to want to take the mass of the first isotope, multiply it by its percentage expressed as a decimal, and then we'll take the mass of the second isotope, multiply it by its percent abundance expressed as a decimal, and we'll add the two of them together. So we will start with gallium-69. So what's its mass? It's the first one here, so respectively, we're going to use the first mass. It is 68.926. And now we want to multiply this by gallium-69's percent abundance, but expressed as a decimal. So we'll be moving the decimal place two spots to the left times 0.6011.
Okay, I'm just going to pause that for a second if you need to write that down. Okay, so that's our first isotope.
That's the first part. Now we're going to want to do the same thing for gallium-71. So its mass is the second one here, 70.925. And we'll multiply it by its percent abundance as expressed as a decimal. Move this place 2 to the left, so we get 0.3989. Multiply both of these together and then add them up.
And I'll just pause again so you can write that down. Okay, and you would do your order of operations here. Do the multiplication first and then the addition.
And what you're going to get is 69.72 AMU for the average atomic mass of gallium. Now, if you wanted to just check your work, you could look gallium up on the periodic table. Here's what it would look like. And underneath the element name is the average atomic mass, which matches what we just calculated. Now, very quickly, check this out. We have two isotopes of gallium. One weighs about 69, the other weighs about 71. And the mass is closer to 69 than it is to 71. And that makes sense because there is more gallium-69, 60%, as compared to gallium-71, which is only about 40% abundant. So it makes sense that our weighted average should be closer to this one that's more abundant than to this one, which we don't have as much of. Rubidium has two isotopes, rubidium-85 with an atomic mass of 84.911 AMU, and rubidium-87 with an atomic mass of 86.909 AMU. The atomic weight of rubidium recorded on the periodic table is 85.47. And in this question, when they say atomic weight, they mean atomic mass, relative atomic mass. Any of these terms you can use interchangeably. Based on this information, which of the isotopes of rubidium is more abundant? And we're talking about, is it rubidium-85 or is it rubidium-87? And how do you know which one?
Pause for a moment before Tyler gives the explanation. You are going to chat with your neighbor. The question is, we know the average atomic mass of rubidium is 85.47. We know that there are two isotopes. One weighs 85 and one weighs 87. Which one is more abundant? What does it mean to be more abundant? It just means you have more of it. Which one is going to be present in a higher percentage? So have a chat with your neighbor and decide, is it rubidium-85 that you have more of, or is it rubidium-87 that you have more of? Oh, and by the way, it was just pointed out to me that when I typed this out, I didn't type 87, I typed 85 twice, so you can change that, okay? What do you guys think? Which one is more abundant, rubidium-85 or 87? 85, why? This mass is closer to 85 than it is to 87. So let's let Tyler chat us through this.
One is more abundant. This is a thought question where you don't really have to do any calculation. And it revolves around the idea of relative atomic mass, atomic weight. So now how does this relate to these two isotopes? Well, we have rubidium-85, which weighs pretty close to 85 AMU. And then we have rubidium-87 that weighs pretty close to 87 AMU. So for these two things, the regular average, if we had the exact same amount of both, would be right in the middle. It would be 86 AMU.
Does that make sense? If we had 50% of each, we would have 86 AMU.
But instead, we can tell from here and from the periodic table that the atomic mass of rubidium, the weighted average, isn't 86, it is 85.47 AMU. This means that it's closer to the mass of rubidium-85. It's not in the middle, and it's not close to 87.
I'm just going to pause it there, so if you want to write any of this down, you can. If you don't want to, that's also fine. Always have to make sure I pause when his hands aren't in front of it. So if you wonder how your grades get calculated, we use weighted averages. So we would take your test percentage and we would multiply by, well, I guess for you guys it's about 0.75. And we take your quiz marks and we would multiply by 0.1. And then we would take your lab marks and multiply by 0.15. And then we'd add those three together.
So that means that the weighted average is telling us that we have more rubidium-85 because this weighted average number is closer to this. So there's more of this that's pulling the weighted average number down. So rubidium-85 is more abundant because the atomic mass weighted average is closer to that than it is to this. Magnesium has 3 stable isotopes.
Okay, so this is on our next page now, so flip on over.
Calculate its average atomic mass using the information in the chart below. We've already done this with 2 isotopes, but you can do it with as many isotopes as you need. It's the same process throughout. So let's start with magnesium-24. We're going to want to take its mass, which is 23.985, and multiply it by its abundance, expressed as a decimal, 0.7899. That was magnesium-24. Now we're going to go on to magnesium-25.
I'm actually going to let you guys try and finish this, and then we'll check our answer with Tyler. Okay? So using that first one that we did as a model, you guys can probably get this one. But if not, Tyler will teach us. What do you think? Are we ready to see the answer?
Take its mass, 24.986, multiply that by its abundance as a decimal, so 0.10000, okay? And then finally, magnesium 26, 25.983 times 0.1101. I fit it all on one line. So we're going to do this math, and we're going to end up with 24.31 AMU is the average atomic mass, and you can check yourself by looking it up on the periodic table, and you find that the reported atomic mass is the same as what we calculated here.
So do you like that? Is that pretty straightforward? All right. Now, if during the rest of this class, if you're getting bored with what I'm teaching because it's something you already know, you could, if you wish, to work ahead on this stuff, but don't worry about this for the rest of today, okay? Could you close that door, please? Thank you, Isaiah. The quiz on this is not until Tuesday, yes? So we just wanted to introduce it today. Next day we'll be doing a little more practice, but we're going to move away from this today after we have looked at the sig figs. So we're going to just take a quick look at the sig figs. So here we go. Here's the calculation that Tyler did. And if we do our order of operations, first of all, we're going to do all our multiplications. Okay. And when we multiply these first ones, we get 18.9458. There might be some decimals after that. I've just left a few extra places on there. But if I want to know how many sig figs are in that 18.9458, I need to look at the sig figs here and the sig figs here. And my smaller number of sig figs is 4 sig figs, which means that this number has 4 sig figs. Will I round off here? No, I'm not going to round off, but I'm going to keep it in my head that there are 4 sig figs. And if there's 4 sig figs, which of those digits is the uncertain digit? Is it the 1, 8, 9, 4, 5, or 8? Who is uncertain? Tell your partner. Who is the uncertain digit? It is the last of our significant figures, so it's that 4. We don't need to worry about whether it rounds or not because we're not rounding it, right? And what position is that in? That is in the 1/100th position, and that's where our uncertainty is. Now, our next number, when we multiply, we get 2.4986. And once again, the smaller number of sig figs in that multiplication is 4 sig figs. So this number up here will have 4 sig figs. So who is the uncertain digit in the 2.4986? The 8. That is our uncertain digit. So we have uncertainty, this time not the hundredths, but in the thousandths place. And our last multiplication there, we get 2.8607. And once again, 4 sig figs. Which means that this number up here should have 4 sig figs. So which digit is the uncertain digit? That would be the 0. And that again is in the thousands place. So when we add it up, remember we do not round off. We use the entire 18.9458. We don't round off to 18.95. We keep that whole number. So we add up all those three numbers, and instead of getting 24.31, what we actually end up to start with is 24.301, or sorry, 51. Okay, so that's what you get when you add those three numbers together. And because we're adding, we now have to go to the first uncertain digit, and the largest uncertain digit is the hundredths position. So we have to say, now we need to round to the hundredths position. And that means we look to the right, that's a 5, so that's going to round up. So that will then round to 24.31 AMU. Okay, so at this point I am going to go through, where is it? Page 54, 3.2F, page 54. But if you feel like you know this already and you don't want to hang out with me, you can work ahead on pages 66 to 67, or you can do review for tomorrow's quiz here. This is related, however, to tomorrow's quiz, okay? So this will help you, especially with the Bohr model part of tomorrow's quiz, okay? If you want to hang out with me and do this with me, there we go. So page 54. First part, just to get us warmed up, an ion is an atom or group of atoms with a net or overall charge. In a neutral atom, the number of protons and electrons are equal. In an ion, the number of protons and electrons are, you could either say not equal or you could say different. Protons have a what kind of charge? Positive. Electrons have a negative charge. If the number of protons and electrons in an atom are not equal, then the atom will either have an overall positive or negative charge. This is called an ion. Oh my God. Okay. Now we touched on this yesterday, but this is just a reminder. It turns out that a filled outer shell is very what? Stable. So atoms will either gain or lose electrons in order to have this stable filled arrangement. What do we call the outer shell? There's another word for it. The valence shell. So a filled valence shell is very stable. Now, we're going to start with anion formation. Those are our negative ions. If you have an atom with 5 or more valence electrons, in other words, it's going to be close to a full valence shell. How many is usually in a full valence shell? 8. Okay, so if you have 5, are you closer to full or are you closer to empty? You're closer to full. You would only have to add 3, but if you had to take away, you'd have to take away 5. So instead of taking away 5, we will simply add 3. Okay, and so this atom would, anything with 5 or more will gain electrons in order to fill that shell. What type of elements have 5 or more valence electrons? What type of element? What are the 2 main types of elements? There's metals and nonmetals. Which kind, metals or nonmetals, have 5 or more valence electrons? That's a tricky one, right? Let's go to our periodic table and make sure that we know this for the future. We did this a little bit yesterday, but we are going to do it again today. This is column number 1, also known as group number 1. If you don't know your columns and your rows, perhaps you know that buildings are held up by columns, which lets you know that columns are vertical because you don't need horizontal columns holding up a building, that they don't work that way. So this is group 1, and everything in group 1 has 1 valence electron. Everything in group 2, can you guess how many valence electrons those have? They have 2 valence electrons. Feel free to write on a periodic table if you have one. I have lots kicking around, so if you want a blank one later, you can grab a blank one, okay? In the middle here, do you guys remember what these elements are called? Those are called the transition metals. The transition metals, they don't have valence electron, they don't have predictable valence electrons. So I would never ask you how many valence electrons are there in iron, because it doesn't work the same way, okay? And if you're like, where could I write this? There is a periodic table at the front of your book on page 1. These do not have a predictable number of valence electrons. So we don't have to worry about this. So groups 3 through 12, don't worry about it. But when we get to group 13, we start having a predictable number again. So group 1 had 1, group 2 had 2, group 13 has how many? 3 valence electrons. And group 14, guess what? 4. Why is it not moving? There we go. Group 14 has 4 valence electrons. Group 15 has 5 valence electrons. 16 obviously has 6. 17 has 7 valence electrons. Group 18 is a little weird. Valence electrons are the electrons in a partially filled shell. What do we know about group 18 and its outer shell? It's completely filled. Therefore, how many valence electrons? 0, okay? So that's going to be a really powerful tool for you. You're going to be able to do things if you know those numbers of valence electrons, like you won't have to use the baby periodic table anymore. Do you guys know the baby periodic table, the one that gives you the charges in every column? It's like, oh, it says Li plus, Ca2 plus. You won't get those this year. You get one that looks like this. But if you know that group 17 has 7 valence electrons, you know that that atom is going to gain 1 to become full. And if it gains 1 negative particle, its charge is 1 negative. And we're going to go through that over and over again until it becomes like in your head. So don't worry if you missed it that time. We will do it again and again until you get it. Okay? So back to page 54. Oh, which ones have 5 or more valence electrons? What type of elements? Metals or nonmetals? Which type have 5 or more valence electrons? Those would be our nonmetals. Nonmetals have 5 or more valence electrons, right? Okay. So those will be our nonmetals. I forgot that's why we were there. So those are all nonmetals. And there's something else which you probably learned in grade 9 and 10, but may have forgotten. When an anion is formed, what happens to the ending of the name? When we have sodium and it gives away an electron to chlorine, we get sodium chloride. So when an anion is formed, the name ending changes to ide. And that will be important. That will be one of the questions on your quiz. You will be expected to name an anion by changing the ending to ide, which is not hard. We'll practice. Okay. Look, fluorine becomes fluoride. Oh, gosh. Was that easy or hard? Easy. Okay? Okay, hard, but whatever. Okay. Now, here is a Bohr model of a fluorine atom. And you'll notice that it has an empty space in its outer shell, right? There's room for 8, but it only has 7 in that outer shell. Fluorine has 9 protons and 9 electrons, so its net charge is 0, which makes sense because all atoms are neutral. But from somewhere, comes an extra electron and fills that spot, okay? And now instead of 9 electrons, we have 10 electrons. We have gained a negative particle. And if we have 1 extra negative particle, the charge is going to be negative 1, okay? So when we write the symbol for fluorine, it's just F. When we write the symbol for fluoride, it is F minus. Now, is there anything else we need to do to this ion Bohr model to make it 100% correct? You would get most of your marks for a Bohr model that looked like that. You could have the number of neutrons. I'm not going to worry about that right now because on the quiz, it'll actually, like, there'll be a little blank and it'll say protons and a blank and it'll say neutrons, so you'll know you have to fill them in. But what's missing from this ion? The brackets and the charge. Yes. Okay. So we put brackets around it saying this whole thing has a charge of -1. And if we were in grade 9, we would spend some time with you thinking about it, but we're just going to barrel on through this. Here is sulfur. Sulfur has 16 protons, and its atom has 16 electrons for a net charge of 0, and its symbol is S. And you'll notice in the outer shell there is a gap right here with no electron in it, and a gap right here. with no electron in it. So what's going to happen is that electrons are going to come in, okay, and we'll end up with one here and one here. So now we still have 16 protons, but now how many electrons? 18. And because we have gained 2 negative things, our charge is 2 negative. And so our symbol would be S2 minus. And we no longer have a sulfur ion. What would it be called? It would be called sulfide. Sulfide. Okay? I don't know why there's that line there. It's accidentally there. Okay. Next one. Nitrogen. Nitrogen. And you'll notice this is one of the ones where they put the 2 on the first shell in a different location from each other. I don't think that is as correct, and I should probably go through and fix that, but I haven't done it yet. Okay, so if you happen to do that, I'm not going to get too worried about it. So we have 7 protons and 7 electrons in nitrogen, net charge of 0, symbol N. How many gaps are there in nitrogen's outer shell? There are 3 gaps, 1, 2, 3. And so we are now going to have 3 electrons fill those gaps, 1, 2, 3. So now instead of 7 electrons, we have 7 plus 3 is 10 electrons. We still have 7 protons. So our net charge, we have more negative things than positive, so the net charge is negative 3, and the symbol will be N3 minus. I do sometimes have people ask me, can I write N minus 3 or N3 minus? N3 minus is the more correct way, but if you write it N minus 3, that's going to be fine. I'm not going to get worried about it, okay? What would we name this ion? Nitride. You'll notice it's nitride, not nitrogide, okay? Not nitrogide. How many syllables in nitride? Do you guys know how to count syllables? Nitride. Yes? Just like in elementary school where they're like, how many syllables, right? Nitrogide would have 3 syllables. Anions, with 2 exceptions, which we're not going to worry about right now, have 2 syllables. Nitride. So phosphorus, that's 3 syllables, does not become phosphoride. What would it become? Phosphide, because there's only 2 syllables in anions. Okay, so basically you take the first syllable and then stick "ide" on the end. Okay, anions have 2 syllables. I'll tell you the exceptions another day, but we're not going to worry about that. Anything that appears on tomorrow's quiz will not be an exception. Okay? Yeah, where do these anions get their extra electrons from? We've got electrons coming in from somewhere, right? Where are they coming from? From the air? From an alternate universe? That sounds like fun. Well, it's not nearly as much fun as that. They come from other atoms. What type of element do you think gives the electrons to the anions? Who wants to give away their electrons? What type of element? Sorry? When I say type of element, you should think two things. Type of element could be a metal or a non-metal. Who wants to give away their electrons? The metals, because if we look back at our periodic table, they have only one valence electron or two valence electrons, or here we have aluminum and gallium, which have three valence electrons. Things get a little weird under the staircase towards the bottom, but don't worry. Will I give you any of the weird ones? No, because the Bohr model does not work for the weird ones, okay? I will only give you Bohr models up to element number 20, okay? All right, here we go. So they come from other atoms. They come from metal atoms. Now we're going to look at cation formation. And this is when we have 3 or fewer electrons. Those are in our metals. In other words, we are closer to empty than full. If we have 3 electrons, we could either add 5, that's too much, right? Or we can just take away 3 and empty out the shell. So those are going to lose electrons in order to leave the valence shell empty, and the new outermost shell will now be full. Atoms with 3 or fewer electrons are all metals. Here's a Bohr model of a sodium atom. It has 11 protons and 11 electrons. Net charge is, of course, 0. And we have this inconvenient electron in the outer shell all by itself. What will the atom do? It will say, bye-bye, and the electron will go away. Okay, and now that outer shell, you can see on the other side, it's empty. Okay, it is a vacant valence shell. So now instead of having 11 electrons, now we have 10 electrons. We have lost 1 electron. And if you take away -1, you get +1. And so that means that our symbol for sodium now is going to be Na plus. We don't have to write the 1. In fact, we normally don't. If it's just a plus, it means +1. And what happens to the name? Sodium, oh, it just stays as sodium. So if you're ever confused about who changes their names, just think of sodium chloride, because most of you are familiar with that, right? Sodium doesn't change its name. It's sodium, but chlorine becomes chloride. So it is only the non-metal that changes its name ending, okay? So there's no change to the metal, no change to the metal name. All right, here we have magnesium. We have 12 protons in the atom, which means we also have 12 electrons. Net charge is 0. Symbol is Mg. Now, if I was doing this in pencil, I would say I've got these 2 electrons here, and they need to go away. So if I were actually doing this on paper with a pencil, I would erase them, but this is printed, so we cannot erase them, so I'm simply going to X them out so that now they're no longer there anymore. Okay, so they're gone. If you're writing a quiz tomorrow and you have drawn those 2 electrons in and you want to get rid of them, you can either erase them, or if you don't want to go through the bother, you can just cross them out. Either way is fine. Okay? What's the name of this ion? The name of the atom was magnesium. The name of the ion is magnesium. Oh my goodness, that was easy. We have still 12 protons. We lost 2 electrons. So we only have 10 electrons now. If we take away -2, we end up with +2. And so we have a +2 net charge, and our symbol is Mg, 2+. Would I get full credit for this Bohr model? What have I forgotten? Brackets and the charge. Let's go back and see if I forgot any others. I think I did. Let's go back. Did I forget it on sodium? I forgot it on sodium. We need our brackets and our charge plus. And what about my anions? Did I remember it on my anions? No. Okay, so I need to put my brackets on here and my charge, and back to sulfur, brackets, and charge. So before you hand in your quiz tomorrow, what are you going to say to yourself? Brackets and charge. Maybe even when you hand it in, I'll say to you, what should you say to yourself? And you'll say brackets and charge. And if you haven't written it down, then you'll remember, and you'll go back to your seat and you'll fill it in, or I'll have a pen here and you can fill it in. Okay? All right. I think there is one more. We have aluminum. For completeness, we have 3 electrons, which can all go bye-bye. Bye-bye. We start with 13 protons and 13 electrons. Net charge is 0. Symbol is Al. We're going to show these going away by crossing them out. We have 13 protons and how many electrons now? 10. So our net charge is 3+. So our symbol is now Al, 3+. And what do I have to do to the name? Nothing, just aluminum or aluminium if you happen to be from anywhere other than Canada or the US. And finally, brackets and 3+. Hooray! Okay. Where do cations send their extra electrons? To other atoms. And look, here we go. We're only showing the valence shell, but here's sodium. It's got this 1 electron here, and chlorine has this 1 space here, and lo and behold, there it ends up, and everybody has now a full shell, which is nice and stable, and everyone's happy. Don't use the word happy. Atoms don't actually have emotions. Now, before we send you off to do some practice, we're just going to take a quick look here. All right. Group number 1 is column number 1. What do you notice about the valence shell of everything in group number 1? We have 1 valence electron. So when group 1 becomes an ion, every single atom in group 1, what does it do when it becomes an ion? They all lose 1 electron. So we're going to show crossing those electrons out. And we would then put our brackets, and all of these would become +1. So just plus and plus and plus. So everything in column 1 is +1. You don't need the baby periodic table anymore. You know there's one valence electron. You know it has to be removed. So you know that everything in column 1 is going to be +1. Column number 2, group 2. How many valence electrons? 2 valence electrons. So 2 electrons go away. What's the charge going to be? It's going to be 2+. And the same thing for magnesium. 2+. And the same thing for calcium. Those 2 outer electrons go away, and we're left with 2+. Let's just do one non-metal group. Okay. Let's do group 16. Okay. Oxygen has how many holes? It has 2 holes, so we can fill those holes in with electrons. And now the charge is how much? 2-. And we can do the same thing for sulfur. We can fill in those extra electrons. The charge becomes 2-. I'm going to let you fill in the rest of this on your own. But before I do, I'm just going to mention group 14. How many valence electrons in group 14? 4, right? 14, 4. And people are always like, oh, do I get +4? Do I add 4? Or do I take away 4? Add 4, take away 4, add 4, take away 4. Normally, carbon doesn't actually form ions. It usually forms covalent bonds. It shares electrons in order to fill its shell. So if you're like, what's the charge of group 14? They don't really tend to form charged particles. They tend to share their electrons instead to get that full outer shell. We will look at that more towards the end of this unit, okay, when we're doing some Lewis structures. So just don't worry about group 14, right? They don't form charges, at least not to speak of, very rarely. And we don't do rare stuff in grade 11, so we're just going to be like, it's fine. They just don't, okay? So I think I have taught you everything I need to teach you for today. So in theory, you know everything for tomorrow. If you wish to practice for tomorrow, the chart questions on page 39, 51, and 53 will give you a good idea of what that first question will be like. What we have done today will help you out with those Bohr model questions. What you did yesterday will help you out with those Bohr model questions. If you want to do all the review for it, you can do all of that, okay? It is all up on Teams as well. And if you're like, wow, I know this already, Ms. Spence, this is boring. I have one student who just finished taking Science 10 last semester, and now they're in Chem 11. And so they just literally did this like 5 minutes ago. So they're like, okay, yeah, I don't really need to practice it. So if you're in that boat, you can work ahead and do some of the, atomic mass. But don't do the atomic mass. Otherwise, just study for tomorrow's quiz, and you're good to go. Alrighty?